We have spent a lot of time the last couple videos trying to figure out how to find areas under standard normal distributions, as well as how to find z-scores when given areas. And so what we're going to do now is we're going to look at some examples of why we learned that. So these are more of our real-life applications of working with normally distributed variables. So we're going to do two examples here. So the first says, suppose that the distance of fly balls hit to the outfield in baseball is normally distributed with a mean of 250 feet and a standard deviation of 50 feet. If x represents the distance in feet for a fly ball, we're asked how is x distributed. We're going to use that shorthand notation. X is distributed. We were told that it was normally. We were given its mean of 250 and its standard deviation of 50. And so that's how x is distributed. Next here, we're told if one fly ball is randomly chosen from this distribution, what is the probability that it traveled fewer than 220 feet? So we're supposed to sketch the graph, which we know is bell-shaped because it's normal. We are sketching the graph of x, where x is our distance, right? The distance of the fly balls. Its mean was 250. And then we're adding increments of 50, since that's our standard deviation. And then we'll subtract increments of 50 as well. Okay, so this one asks us, what is the probability that if one ball is chosen at random, that it traveled fewer than 220 feet? Well, 220 is right down here. And fewer than 220 means we're looking below it, so to the left. We're looking for this area. So this is a case where we are given a value. We are looking for the area that is going to be normal CDF. So we're going to second distribution, normal CDF, our lower value. Remember, this is the leftmost value where we start collecting area. So in this case, we're extending to negative infinity. So we're going to type for lower there, negative 1,000,000. Our upper value is where we want to stop finding area. So that's 220 in this case. We have not standardized this variable. This is not z, this is x. So we need to type in for mu, the mean of x, and for sigma, the standard deviation of x. So our mean was 250. Our standard deviation was 50. And we will get there 0.274253, taking that to 4 decimal places. We have 0.2743. And so what we know is that about 27.43% of all the fly balls are going to go fewer than 220 feet. Right, and then we're going to do one more part to this example before we look at another example. This one says, find the 80th percentile of the distribution of fly balls. So what does 80th percentile mean? If you remember, the percentile represents the percentage of values that are below your value. So the 80th percentile would mean that 80% of values are below that value. So we're somewhere up here where this is 80%, 0.80. And what we're looking for is, well, what is that value, right? What is the length of, this is still distance of fly balls. So what is the length or the distance of that fly ball that separates the lower 80% from the upper 20%? This is one where we are given an area. This is using inverse norm. So second distribution, we're choosing inverse norm. The area, remember, should always be area to the left. In our case, that's what we have. So the area to the left was 0.8. Our mean was 250. Our standard deviation was 50. And what we get there is 292.081. 06 and so forth. And so the 80th percentile would be 292, we'll say 0.08. That's in feet. This one we were asked to interpret the meaning of our answer. So we would say 80% of fly balls travel fewer than 292.08 feet. Okay, so that would be our interpretation. And we're going to look at one more example. So doing the exact same thing, just doing one more example so we feel really comfortable. So this time our variable of interest is IQ, and we're told that IQ is normally distributed with mean 100 and standard deviation 15. That's always the case for IQ, so it gets constantly standardized so that it has a mean of 100 and a standard deviation of 15. And we are told to suppose we select one individual at random, and X is going to represent the IQ for that individual. So how is X distributed? Well, again, we are told here that it is normal. We're told its mean is 100 and its standard deviation is 15. So what we want to do in part B is find the probability that a person has an IQ greater than 120. So our normal distribution here for X, where X is the IQ score, is, we know, centered at 100. With standard deviation 15. And so the curve looks something like that. And we want the probability that the person has an IQ greater than 120. So 120 is down here. And if we want the IQ greater than 120, that's up here in this right tail. We are given a value, we are looking for an area. So that again is normal CDF. Our lower value this time is going to be the 120. That's where we want to start finding area. Our upper value is going to be 1,000,000. Remember, we're just extending to positive infinity. Our mean is 100. Our standard deviation is 15. And we get there 0.09121128, etc. So to 4 decimal places, that's 0.0912. So what we're saying is about 9.12% of the population is going to have an IQ greater than 120. Moving on here to part C, we are told that Mensa is an organization whose members have the top 2% of all IQs, and we're asked to find what that minimum IQ score is that you need to qualify for Mensa. So again, we're looking at IQ scores. We know they're centered at 100. And what we're being asked this time is, well, what's the IQ that a person would need to have only 2% of the IQs be above their IQ? So we know that's going to be way out here somewhere. But we don't know what that value is, right? We know that the area to its right is 0.02, 2%. And we have to find the value. If we are given area, that's an inverse norm. Remember in the calculator, for inverse norm, we have to enter the area to the left. So if the area to the right is 0.02, the area to the left is the other 98%, right? The other 0.98. And so for inverse norm, under area, we're going to type in the area to the left, which is 0.98. The mean is still 100. The standard deviation is still 15. And we get 130.80623. And so basically we would need an IQ score of about 131, right? 130.8 to qualify for Mensa, to be in that top 2% of all IQs. The last one here says the middle 50% of all IQs fall between what two values? So we're still looking at IQ. We still know that it's centered at 100. This time I want to find the two values, and again, I'm just going to call them for now. I'm just going to call them x1 and x2. I want the two values that divide my curve up into a middle area of 0.5, so 50%. Okay, if 50% is contained within these two x values, that means there's another 50% that is not, and that other 50% is split equally between two tails. So I have 25% of the area in each tail and 50% in the middle. The reason that matters is we're going to have to do this twice. We need two x values. So inverse norm, the first value right here has an area to its left of 25%. So area is going to be 0.25. Mu is still 100, sigma is still 15. And we do that, we get an x value of 89.88. And then when we do it one more time, for x2, this time the area to the left of x2 is this 50% plus the other 25%, so 75%. Mu is still 100, sigma is still 15. And we get 110.12 as our other value, okay? And so we would say 50%, the middle 50% of all IQs are between 89.88, or basically 90, and 110.12, or basically 110.